And there we go. Okay, so I think everyone should be able to see my screen now. So thank you for the intro, Emily. My name's Jonah. I'm a second year grad student at Northwestern in the chemistry department. And the past couple weeks, I've had the pleasure of learning about machine learning more, and I'm excited to tell you all about it. But before I jump into that, just a little bit about myself. So I put some of my hobbies here, some things about me. One of my big hobbies is playing chess, which has been actually wonderful during the pandemic, since this didn't get interrupted at all. I can just play online all I like. It's great. Moving down, you can see that I'm from Boston. I've lived in Massachusetts for pretty much my whole life until I started grad school here. So I'm definitely excited to be somewhere else and be in a new big city, but also missing Boston. I put a little picture here. I've got a picture of my research group over here, and I'm kind of in the back left corner there. And probably one of my other favorite hobbies is rock climbing. Now, I wish this was a picture of me. This looks like a beautiful place. Unfortunately, I couldn't dig up any pictures of myself rock climbing, but that's more about me. And then this strange looking thing I have in the center is just a figure I made related to my research that took me way too long to make. So now I feel like I need to show it off whenever I can, because I spent too many hours trying to make it look right. But anyways, into the details. So what is machine learning? And that is something that I also didn't know in much depth until very recently. But it's a subset of this field called artificial intelligence. And artificial intelligence is this kind of catch-all umbrella term to describe any time that you've got a computer that is somehow emulating human intelligence. So, like I said, that's really a catch-all term, but probably the type of artificial intelligence that we hear about the most is machine learning. And machine learning is a more well-defined concept. And the idea of it is to create an algorithm that can self-correct to become better at whatever its task is. So an example that is pretty relevant both to societal applications and makes for nice analogies is image recognition. So for example, one thing that machine learning algorithms do a lot is try to recognize people's faces. So a machine learning algorithm would somehow take a bunch of images of people's faces, and it would kind of be able to teach itself and correct the parameters that it has running within it so that it can get better at recognizing faces over time. And then deep learning is this kind of subclass of machine learning, which is kind of just a natural evolution of machine learning, but basically it is a more complicated algorithm that has more layers of abstraction to it, but it's capable of achieving a lot more. So a standard machine learning algorithm, if I was trying to teach it to recognize a face, I would tell it to check if there are two eyes, if there's a nose, if there are eyebrows, so on and so forth. And me as a programmer, I'd actually have to input those features, and I'd have to tell the machine to look for those things. And then over time, it would work to try and figure out which of those are the most important in determining whose face I'm looking at. A deep learning algorithm, though, is special in that I don't have to tell it what features to look for. It's going to be able to learn those features all by itself. And that is really powerful. And that's one of the reasons why this technology has become so heavily used in society today. So taking a step back, I mentioned the phrase algorithm a couple times in the last slide. And typically speaking, I think that, well, the words algorithm and program are kind of interchangeable, but in traditional programming, the way that you set things up is like me as a programmer, if I'm doing something for my research, I'm going to write some program and I'm going to give it a set of rules to follow. And it's going to follow those rules and just repeat them consecutively until it reaches some answer or some result. So, I just tell my program what the rules are, I can feed in data, and it's going to spit out answers. So that's traditionally what happens with programming. But with machine learning, this whole setup kind of gets flipped around, where in machine learning, you don't actually tell the program any of the any instructions. What you do is you give it a bunch of data and you tell it what the answers and results are prior to it doing anything. So it kind of solves the inverse problem where it's going to take all the information and it's going to try to deduce the rules that you would have written. So in the context of recognizing an image, say you've got an algorithm that's trying to determine if something is a tree, you would give it a bunch of data, which would be pictures of trees and bushes, and landscapes, and all sorts of things. And you would tell them, the algorithm, whether or not those are trees or not. And over time, it would come up with a set of rules that it can follow to determine for some new image if it has a tree in it. Okay, so that is what's called the training phase. When you're just.
Can I ask questions?
Yeah, absolutely.
Got a diagram there, and on the left, it has answers, results, and data, and on the right, it's not covered. Seems to me what happens on the right depends on what you put on the left.
Right.
Unless there's another arrow coming. What comes out on the right can't be any better than what's on the left.
That's a good question. So yeah, and that raises a good point. The instructions that you get out are only going to be as good as the data and that you can feed in. So if I'm trying to train some algorithm to, recognize whether there's a tree in a photo, I better have some pretty clear photographs and good examples, right? So that is one of the real challenges of implementing machine learning into a in real applications. Because in theory, it's totally fine if your machine learning algorithm doesn't perform great. But if you're going to use that to help run your business or something, then you better make sure that you're feeding it quality data. So yeah, that's an excellent point. I don't know if that answered your question though.
Keep going.
Awesome.
Have another drink?
Okay, so like I was saying, that's the training phase. And then once you're done with that, you can move into the production phase. Your set of instructions is converted into some model. And now you can just feed in data. You can give it new pictures. It's going to be able to identify what's in those pictures. So that's the very general outline. So here's a kind of cute example. So I've been referring to this idea of image recognition. And basically, this is an algorithm or a machine that could maybe differentiate between dogs and cats. So I'm just trying to illustrate here that with a standard machine learning algorithm, I would have to feed in individual pictures of these animals, and I'm going to test a bunch of different features like the size of them and the shape of their ears. Cats have pointy ears, dogs' ears are more droopy. I'm going to ask it whether or not it has whiskers, and my algorithm is going to, weight all of these variables in a way so that when I give it a new picture, it's going to be able to figure out whether I've got a dog or a cat. And this gets a kind of like an abstract way of drawing it. So we define these things, these circles called neurons, and they're not neurons in the sense of neurons in your brain. They're kind of a loose abstraction there, but imagine you've got a picture, it's got a bunch of pixels. So all these circles on the left are one of those individual pixels. And then all these circles in the center are some neuron representing one of these features. So if this top one was the feature of, how big is the animal, it's going to take some input from every one of these neurons. And it's going to come up with some estimation of what's the size of this animal. And it will do that for every feature that I tell it. So I think the next example I had was whiskers, whether they are there or not. And it will do that for all of them. So you get all these connections, and this algorithm, as it runs, it's going to start recognizing whether these features are present. And it will use that to determine if you have a dog or cat. And once it receives some validation that it's either correct or incorrect, it will go back and kind of reweight all of these lines and make some of them thinner and some of them thicker so that it can more accurately make predictions.
Question.
Yes.
You said wait.
Yes.
Is that done objectively, or is there? That sounds like a tricky part of this, is to how you decide how to mix those things together.
Yeah. So when I say weighting the different features, I mean you're or the algorithm rather has to decide how important each of those features are. So it might over time decide that, knowing the size of the animal doesn't do a great job of differentiating between dogs and cats, because we've got all these really tiny lap dogs that exist, and the size doesn't really make a difference there. So it might decide that going from this top neuron that talks about the weight, it might make these lines really thin so that they don't have much influence on the final decision-making process. But yeah, that is the really tricky and technical part of it, is like, how do you reweight these things? And I'm not going to get into all of that, but it's the kind of stuff that I think is interesting, but it's probably over my head in terms of how technical it is.
But you do trust it once it does come up with its answer.
Yeah, so you have to, so if I go back a couple slides, right, once you get through this training phase, you're going to go and test it on a bunch of different data where you know the answer, and you're going to just measure how often does my model do the right thing. So if it's making predictions correctly, like 99% of the time, you'll probably go ahead and use it depending on what the application is. If it's really doing a poor job of making predictions, then you've got to restructure things in some way, because obviously you want your model to be working well. And there's a lot of intricacies in terms of how you actually build these neural networks. There's a lot of different strategies for doing that so that you can optimize performance for different applications, with the most common applications being image recognition, voice recognition, things like that. And actually, one of the ways that these algorithms can get better is through deep learning, which is really the same thing, except instead of having a single layer of neurons like we had before, where each neuron is a feature that the programmer has to input, you've now got these sets of hidden layers. And I didn't draw every line here, but I just drew kind of one path through this network. And the strength of this is that it becomes a lot better at recognizing things. It's able to extract new features that you haven't even told it. And two, it has, because of this structure, it's basically just becomes more accurate. So this is like the technical difference between standard machine learning and deep learning, is the number of layers you have here. Now, the more qualitative difference is that deep learning, like I said, can recognize features all on its own without being told. And because of that, it's a lot more powerful, and you can use it for pretty advanced applications. For example, like on your cell phone, Siri learns to recognize your voice over time, and she's doing that through a deep learning algorithm. And The only reason that works though is because it has tons and tons of training data, right? It hears your voice every day. So it can learn pretty quickly because of the amount of data it's getting fed to it. Machine learning, on the other hand, the more kind of rudimentary style, uh, doesn't require nearly as much training data. So they're both useful. It just depends on the application. If you've got some problem you want to handle where you really don't have loads of data to be feeding it. For example, in my field, chemistry, a lot of people are interested in using machine learning to predict whether or not a reaction is going to happen or whether or not like a drug will be effective. In those cases, uh, you just don't have enough training data to run a deep learning algorithm. You could maybe hope to do some machine learning, but you don't have nearly enough data to do deep learning. On the other side, like with the example of Siri recognize your voice, you just have so much data that it's going to be able to learn to recognize your voice specifically, regardless of any accent or what have you. It will just become really well acclimated to whatever data you feed it, so long as you have enough. So here's one question: where is this used in society? And I just put a bunch of random companies here because you can confidently assume that every big corporation is using machine learning or deep learning in some capacity. Now, there's a couple examples that are more standout than others, but uh, the technology has matured to the point that it really anyone can find a use for it. So one of the reasons for that is that it's only maybe in the last 10 years or so that we've had this kind of explosion of data that's available. So with everything being online, it's really easy for a company like Google to start collecting data on you, and then using that data, it will figure out, what advertisements should I show Jonah this week? What is he most likely to click on and then buy? So that's kind of the reason why this has only come into society fairly recently. These ideas about machine learning have existed since, I believe, the 70s, but they're only recently becoming very applicable. One hallmark example is Tesla. So everyone knows about Tesla's self-driving cars, and those actually use deep learning algorithms to be able to recognize features on the road and make decisions. And it's a pretty cool, but also kind of scary concept at the same time, that just the same way that a 16-year-old who's learning to drive for the first time would, initially be really timid behind the wheel, would be making decisions too slowly, and would probably only be comfortable driving around in a parking lot for their first time driving. That's also how these deep learning algorithms start. But as they get exposed to more data, so just video of from the perspective of a car driving, as they get exposed to more and more data, they become more confident in being able to anticipate other people's behaviors on the road and being able to uh, adjust accordingly and react to all the kind of unexpected things that couldn't be programmed in explicitly. So I think that's probably one of the most impressive applications of deep learning, is the fact that you can actually train it to drive a car. So, something totally non-trivial. And so this is all really great. I think this stuff is very cool. It does have some interesting implications for society and policy that are unfolding now and will certainly continue to be issues in the future. And one that's a big deal is, and will probably become more of a big deal in the future, is this just taking away jobs from humans? Because there's a lot of jobs that a machine learning algorithm could do just fine. If a machine can drive a car, maybe soon it can drive a truck, and you don't need to hire truckers anymore. Certainly, phone call services like customer service representatives and whatnot are currently being replaced by various machine learning algorithms and will continue to be replaced in that way. And you can imagine that there's a whole host of jobs that are kind of reliant on just pattern recognition and are maybe fairly repetitive, that used to be occupied by people, but as time goes on, will be more and more occupied by AI as it becomes more capable and affordable. So that's one of the big issues, and it's thinking about how do you deal with the fact that a lot of jobs are going to get occupied by AI. Another issue that comes up is, like one of you mentioned, you need to have good data to make a good machine learning algorithm. And if data is the requirement for having a successful machine learning algorithm, and some companies going to make a fortune on that, well, then there's a question of who owns that data. Is it Google, who mined my data and they figured out that they should advertise cheap cookware to me because I like to cook? Or is it me who, went and watched a bunch of cooking videos online and, I provided that data? So there's some kind of ethical concerns there. Another concern that comes up is privacy issues. And I think this one is another big one that because there's suddenly a need for collecting data on individuals, that does cause privacy concerns because you don't necessarily know who's gathering data on you or how it's being used. And I think for most people, we're pretty content to just live our lives and not worry about that stuff so much. But it is something to think about. And the last one's just kind of a silly point. Are artificial intelligent robots going to take over the world? And I don't think so. I think that's still a sci-fi issue. I don't think that any of these machines are smart enough to decide to go out and train themselves in work domination.
Change batteries.
I'm sorry?
Nothing, just saying you can pull the plug.
Yeah, exactly. Just throw some water on them. Okay, so I think I'm about a minute or two over, so I don't want to cut in too much. So if you guys have any questions or comments, definitely let me know. And
Hey, they just landed on Mars. What part did all this have to play in that?
Wait, what part does machine learning have to do with us landing on Mars?
Oh, they just landed, yeah.
It's happened.
That is a tough question. I'm not prepared for that one. I have no idea what role machine learning plays in us landing on Mars. But it's definitely something that I might look into. I'd imagine that we probably have a video camera on the rover, right? And there's a person controlling it. So I don't know. I'm sure they're using it in some capacity, but I have no idea how.
What company sponsored it? Was it Macy's or was it Ford?
Oh,
Sorry?
no, variety of companies.
I'm just wondering.
I think I had Ford as the car company that was there, but I think it's really all sorts of companies. So a really common example is like if you had a bunch of job applicants and you're trying to select one, it would really make sense to filter out those applications through some sort of machine learning algorithm before you have a manager then go through applications. You could probably filter out a section of them just by some machine. So definitely companies are doing things like that.
Go back to the question as to what did artificial intelligence have anything to do with a landing on Mars? Let's turn around. Let's say that we don't know that. But how about all the data that's coming back? Is that going to be filtered through all all these algorithms, they'll kind of learn more about what's up there. So not what's put in the land, what are we gonna do with all the data that comes back?
Careful.
That's a really great question.
Yeah.
I don't know what we would do with that data. Man, that's a tough one.
Okay.
Okay.
May
I
I?
have, I have no idea. I'm sure that people are up to some exciting stuff, but I've got no clue.
May I, Jonah, if I may intercept?
Absolutely.
I can imagine that NASA's using some of like the machine and deep learning to like allow these rovers to like recognize just like landscape, bodies of water, rocks, and from shapes and other data they have probably fed, and from images they can probably, no one's manning the rover 24/7, I imagine. I'm sure they have a feed on it, but no one's like inputting data. And I think from like both the moon and Mars rovers, they kind of roam by themselves and just kind of explore in a way, unless they have a specific task, I think that these NASA scientists tell them to do. So there has to be some sort of machine learning, sort of recognition that they use to kind of recognize, oh, this is a moon rock or this is a Mars rock, and I'm near a body of water now, and send that data back to NASA. In which they can use that type of data to tell the rover, oh, go here, collect that, bring it back, type of deal.
I think that's part of the answer. They're gonna have all the stuff gonna come in, and they're gonna try to figure out how it relates to something we know on Earth.
Yeah.
Exactly. Yeah. It's cool.
But we'll see.
Awesome. Great job, Jonah.
Thanks, Emily. And thanks to everyone in the audience. Really glad you guys had engaging questions. That was awesome.
So we'll go ahead and switch now to Catherine.